So today's video is concerning the Hantek 20:1 attenuator. I did a previous video where I showed how to use the attenuator along with some high voltage leads and an isolation transformer to be able to measure the mains or the 120 volts AC voltage coming out of your wall outlet. Today I'm going to go a little more in depth specifically on the attenuator, how it works, how it does what it does, and hopefully you can learn something from this. So let's start with what the Hantek looks like, or what the attenuator parts are. It's actually very simple. Let's start with a close-up diagram. Here I drew a very simple diagram. It's just looking at the attenuator end on. So if you look closely, let's see if I can get a pointer here. Here we go, this works. In the middle you'll see like a little copper or goldish female pin, and of course you see this ring around it. The copper or goldish pin is the positive input, and this would be the negative input. This side here is the input, and this side here is the output. And if you look at the opposite side, you can see it's pretty much the same, other than the center pin being a male pin, and of course you have still the same ring, which is a bit smaller than the inputs ring. So yeah, that's pretty much it as far as what it looks like from the outside. It's not very complicated. It plugs into the Hantek like this, and as you can see, this end here looks pretty much identical to the ends on the Hantek itself, and that's on purpose because whatever you can plug into here, you should be able to plug into here. So let's see what is inside of this attenuator. Here I drew a fantastic, beautifully drawn schematic of the inside of the attenuator. You can see there's not much in there. The black, just so you know, the black is the body. The blue is the ring, the rings that are here, and the orange is the copper or goldish pin on either side. And I should probably write here input and output. Okay. So here we have two resistors. One resistor goes straight across between the input positive and the output positive. Oh, by the way, I didn't mention that on both sides the center pin is going to be positive and the outer is the negative. So this is going to be your positive input, and this is going to be your positive output. And this is this ring right here. Although it looks like two separate parts, it's just a representation of the ring around the inside of the attenuator. So just know that these two blue, they're the same thing. They're connected internally. So we see one resistor on between the two positive inputs and outputs, and a resistor between the output side positive pin and the negative rail, which I could have drawn it either way, but I just decided to draw it this way. But just know that this here is connected to the outer pin through this same resistor. So this is a little odd configuration, but this is something that's called a voltage divider. And along with the resistance inside of the oscilloscope itself, this is what helps, or this is what divides the voltage by 20. So let's see a little more detail of how this looks. Another fantastic drawing. This is just a miniature version of the drawing I showed you before, but here I'm showing the inside of the Hantek. So inside of the Hantek, let's see, say this is channel 1 here. You have the center pin again, you can see here, which I represent in orange, and that pin goes to one side of a resistor, and then on the other side of the resistor it goes to the negative or the negative ring here. So that's pretty much it. That's all that's inside of the Hantek. I mean, of course there's more that measures the voltage, but this is the important part as far as we need to know for how the attenuator works. So let's start with a little bit of a lesson on how resistors interact with each other. We're going to look at series and parallel resistors. So here I have an example of some series resistors. Let's write it out. Series, and here is parallel. So examples of some series and parallel resistors. In series resistors, what we have here, what I have drawn here, is some kind of voltage source, a battery, whatever, solar panel, it doesn't matter what it is. Here producing 1 volt. And of course also the voltage is just arbitrary. It doesn't really matter for our purposes here. So just know that this is the positive side here. And this is the negative. Let's write on all these. And conventional electric theory says that the electricity comes out of the positive, goes through the resistor, will go through this other resistor, and then go back to the negative. In a series circuit, the electricity has absolutely no choice. It cannot take another path. It has to go through one resistor and the other resistor. Because of this, the resistances here, the value of the resistances, are additive. You will add the resistance in a series circuit. So here's the equation. RT, or resistance total, equals R1 plus R2, and then however many resistors you have. So this could be infinitely long, or whatever it is. So let's do that real quick. So we have RT equals R1 8 plus R2 10 equals 18 ohms. Very simple, not complicated at all. This circuit here would be equivalent to a circuit that had one resistor that had 18 ohms. It would be exactly the same thing as far as the circuit is concerned. It would be the same amount of amperage, it would be the same voltage drop between this point and this point. It's identical. Now, as for parallel resistors, it's a little bit different. As you can see here, in a parallel resistance circuit, the electricity also flows from positive, conventional electrical theory, and now it has a branch here. It has 2 options. It can either go through this resistor or through this resistor, and depending on which one it takes, since it has 2 options, the total resistance of this part of the circuit is actually lower than both 8 and 10. Since they don't have to go through both, it can actually go through either or. The total or equivalent resistance is less than 8 or 10, and is represented by this equation here. 1 over RT, or R total, equals 1 over R1 plus 1 over R2, go on forever, however many parallel resistors you have. So let's do that real quick. 1 over RT equals 1 over R1, 8, plus 1 over R2, 10. Just take our handy dandy calculator out and do this math very simply. So parentheses 1 divided by 8, or 1 over 8, plus 1 divided by 10, again parentheses, 0.225. So 1 over RT equals 0.225. A little bit of algebra. Let's see. Multiply both sides by RT. We get 1 equals 0.225 RT. Divide out 0.225. RT, or total resistance, is 1 divided by 0.225, which, let's do the math. 1 divided by 0.225. 4.44444 repeating. So 4.4 repeating, which, if I remember correctly, is 4 4/9. I like that better. I don't like the repeating decimal. 4 4/9. Which means that this part of the circuit, the total resistance, or the resistance from here to here, is actually 4 4/9 ohm. Less than 8, less than 10. So we can actually redraw this, or imagine it as this circuit here with one resistor, and that resistor is 4 4/9 ohms. I don't believe that's a standard resistor, but there it is. That would be the equivalent resistance here. Now, I showed you all this to just to give you a quick review, and I wanted to show you this here. This is an example of what the attenuator and the Hantek look like together. This part here is the attenuator. If you look back at the diagram earlier, it's just a positive input here, positive input through one resistor going to the output of the attenuator. The same thing here, one resistor from the input of the attenuator to the output. I should probably write these down. Let me write down, let's see, you can put A in, A out, and we put S in, stand for scope in. Same here, S in, A out, A in. So this is the attenuator input, attenuator output, attenuator input, attenuator output, which is also the scope input and another scope input there. So if we look at the diagram again, this would be the attenuator input and the attenuator output here, and the of course the negative attenuator input, and of course the negative attenuator output. And we can see it's the same thing. One resistor from input to output, and then a resistor across the orange and the blue here, and the same thing, a resistor across the orange and the blue on the output side here. So this is pretty much the same thing as this, just drawn a little bit differently. And here's something that we didn't see before. Inside of the Hantek, there is a resistor, and this we're going to call R3. So here we can see it's a amalgamation, or a set of parallel resistors with one resistor in series. Now, what we want to figure out is when we have a certain voltage here coming in from the leads, what will the voltage at this point be? Because this is the important part. This is the input to the scope. So whatever voltage we have here, we need to have it divided by a certain amount by the time it gets here. Now, since this is a 20-to-1 attenuator, we expect the voltage here to be divided by 20. And well, we're going to show this right now. I've already taken the liberty of measuring the resistances. I'm actually going to show you anyway, so you can see what it looks like. I'll go to high resolution. So if we look at the attenuator, we have between the positive attenuator input and the positive attenuator output, there's one resistor. So let's measure what that is. We're going to measure between one positive and the other positive, and we get 1.0022, approximately 1.0021. I wrote 1002.7 because we're going to be measuring in kilo ohms. This right here is in mega ohms, but you just have to multiply by 1,000 to get the kilo ohms. So that's what the value of R1 is. The value of R2 you should be able to get by measuring the resistance between the attenuator output and the positive attenuator output and the negative attenuator output. So let's do that too. And we get 55.81. I wrote 55.77. I think it's maybe a little bit different because of how I'm holding the leads, or maybe the temperature. Anyway, it's pretty close. So that's the value for R2. And the value for R3 is not within the attenuator, but it's within the scope. And this part is important because this is all part of the voltage divider circuit. This Hantek attenuator is designed to work with this scope. So the resistance in here is just as important as the resistances out here. So let me get the scope. We'll go to channel 1. That's the one I'm reusing. And we're going to do the same thing. Let's see what we get. Get a good connection there. We get 1.3426 mega ohms, or 1.3426 million ohms, which is the same as 1,342.6 ohms. And I have pretty close here, 1,344.7. I measured these earlier, a little bit different, but it won't make much of a difference as far as the math is concerned. So we can use the same equations that we used for the other circuits. Let's see what I did with those. Here it is. So let's figure out where we need to find the voltage. So we need to know what the scope input is. So we need to know the voltage here. So since this is a voltage dividing circuit, we are going to use the equation for the voltage divider. And it's actually a very simple equation. I'm just going to use this corner here. If you want to know what the voltage will be at any point in a circuit, you use this equation. You use voltage total, or the voltage of the battery, or whatever it is you're measuring, and you multiply that by the resistance after the circuit divided by the total resistance of the circuit. So we're going to use this equation of VT times RA over RT. Write this here, VT times RA over RT, to find out what the voltage will be at this point. So what is the voltage total? Well, we're just going to use the number 1 because it won't affect any of the math, and it'll make it much easier to understand. So we're going to do 1 times the resistance afterwards. So what is the resistance after this point? Now you might say it might just be R3, but there's 2 ways to get to the negative part. You can take R3 or you can take R2, and this is the point of the attenuator. It can take both paths. So here we have a parallel circuit. So now we have to use the equation for a parallel circuit. So we're going to have to leave this alone for now because we don't know what the equivalent resistance for R2 and R3 is. So let's go back to the parallel circuit equation, which, remember correctly, it's 1 over RT plus equals, well, we're going to be using R2 and R3, 1 over R2 plus 1 over R3. Let's get our handy dandy calculator out. Let's see. That's going to be, open parenthesis, 1 divided by R2, which is 55.77 kilo ohms. We're going to ignore the kilo because as long as we're using the same units, we can just use the number itself. 55.77 close parenthesis plus 1 divided by R3, 1344.7 equals this ugly number. So let's call that number X for now, just for the sake of the math. Let's call this ugly number X. So we're going to have 1 over RT equals X. We're going to multiply both sides by RT. That'll give us 1 equals X times RT. And then we divide both sides by X. We have 1 over X equals RT. Luckily, this function saves, this calculator saves the last answer. So since this value here is X, we just have to do 1 divided by, and then I hit the button answer, and it gives me 53.5491078. We're just going to go to 3 digits. We're going to say RT equals 53.549. Now what this means, and let's do kilo ohms. Now what this means is that this part of the circuit here, these 2 parallel resistors, even though one is 1,344.7 kilo ohms and the other one is 55.77 kilo ohms, in parallel they're equivalent to one resistor that is 53.549 kilo ohms. So now we have a much simpler circuit here. If we were to replace these 2 resistors with 1, if we just cross this out here, and replace these with one simple resistor, that is this value here, we're going to call it R4, let's call it R4, then this becomes a simple series circuit. Now we only have R1 and then R4. So we can use this equation now. So here we have voltage total, the resistance after, which is these 2 resistors, which we found out is the equivalent to R4, So resistance after is 53.549. Divide that by the resistance total. The resistance total of the circuit, since it's a series circuit, we just add them up, R1 and R4. That would be, R1 is 1002.7 plus, again, 53.549. Just throw this all into the calculator. Let the calculator do the work. 53, sorry, let's use some parentheses here. 53.549. Divide that by, open parenthesis, 1002.7 plus 53.549 equals 0.0506. So, voltage total times this value will give you the new voltage here. And it looks like whatever, let's bring this down here. Voltage total times the resistance after divided by the resistance total, which we figured out is 0.0506. This is pretty much very, very close to just being 0.05. Let's call it 0.05, which we know 0.05 is the same as 1/20th. So this means that you would take the original voltage, whatever voltage is coming out, being measured by these leads, multiply by 0.05 or multiply by 1/20th, which is the same as voltage total divided by 20, and you'll get the new voltage here. So this is how the Hantek attenuator divides the voltage. It uses two resistors along with the resistance inside of the scope itself to divide the voltage by 20. And that's all there is. It's simple, two parallel resistors, one resistor in series, and that's it. That's all there is to it. Now, there's one thing here that I would like to mention. This blue, or it would be the negative lead, has a direct connection to the negative side of every part of this circuit. So whatever voltage you put to this lead here will be on every negative part of the Hantek, since all of these negatives are tied together, as well as the negative of the USB. So that's just something to keep in mind. Whatever voltage you put here will be present at all these points. So that's why it's always a good idea to reference the negative lead to ground. Just place it, if you're working on a car, for example, always place the negative lead at chassis ground. This way, all these reference points will be, all these metal parts, these external metal parts will all be referenced to chassis ground and will be perfectly safe. So if you guys had any questions, any comments, if I wasn't clear about something, you want me to go over the math again, whatever you need, let me know. If there's any other types of videos you would like, specifically concerning electronics, I will be more than happy to do that too. I'm going to continue doing more Hantek videos, and thanks for watching, guys. Appreciate it.